Hi friends, welcome to this 10th video in the series of group theory. In the last video, which was the 9th one, we saw the definition for a binary algebraic system with two binary operations, namely ring and field. This video will give you an problem which is going to define you clearly the concept of ring and field. Come on, we will move into the problem. Prove that Z, the set of integers with respect to two binary operation. One is called as plus circle and the other one is called as dot circle. Is going to be a commutative ring with identity where the binary operations plus circle and dot circle are defined for any elements a and b belonging to the set of integers as a plus circle b is a plus b minus 1 and a dot circle b is a plus b minus ab. So we have two different binary operation which is different from that of our usual addition and usual multiplication. So we are going to show that it is going to be a commutative ring with identity. The first things first, to show that it is going to be a ring. Now I need to show that it is going to be Z with respect to plus circle is going to be an abelian group. Next, second condition, Z with respect to dot circle is going to be, what are the things? It is already a associative law is going to be true. Associative law is going to be true, that is semi-group. And along with it, what are the things added? You need to add an identity element to it, and also you will have to add commutative law to it. So with respect to dot, this is going to be the concept. And the third thing is you need to show that distributive laws are going to be true, which means that what we say about distributive law is a dot circle of b plus circle c will be the same as a dot circle b plus circle a dot circle c. And so the second one will be a plus circle b dot circle c will be the same as a dot circle c plus circle the other way around b dot circle c. So if all these quantities are shown to be true, then I can show that the problem is done. Now this, just notice that this is going to be the conditions that are going to be satisfied for my integral domain, because I know that the inverse element is missing over here. So the problem can also be stated like, show that with respect to Z plus circle and dot circle, it is going to form an integral domain. Now if one more component is added to it, namely inverse is added to it, you can also have one more question added up to the same problem, like you can have to show that it is going to be a field. So when you have inverse to be added with respect to your dot circle, the problem can also be converted to that of a field. The third change which can be done to it is, with respect to plus circle and with respect to dot circle, separately they can ask you to show that they are going to be abelian groups. Abelian group. So with respect to one binary operation, you need to verify all the laws for abelian group. With respect to the other binary operation, this separate can be one problem and this separate can be one problem. So the same problem can be for commutative ring with identity, it can be an integral domain, it can be an field, it can be an abelian group with respect to plus circle, and it can also be an abelian group with respect to dot circle. So many alterations can be done in the same problem, but the base is going to be the same. So what are be the criteria which they have asked for? Start proving for them one after the other. So now we will begin with the plus circle, which is going to be abelian group. So with respect to plus circle, a plus circle b has been defined as a plus b minus 1. A plus b minus 1. The laws to be proved are going to be associative law. I need to show that I have an identity element, I need to show that I have an inverse, and I need to show that commutative law is going to be true. Okay, so if all the four are going to be true, then I can say that it is going to be forming a abelian group with respect to this z and dot plus circle. Okay, so this will form a abelian group with respect to z and plus circle. Now coming to the commutative law, we will see that a plus circle b is going to be a plus b minus 1. Now a and b are going to be taken from the set of integers. So a plus b is the same as b plus a. So what will be b plus a minus 1? This will be the same as b plus circle a. So what happens? Commutative law is going to be true over here. Now coming to my associative law, what will be associative law? A plus circle b plus circle c must be the same as a plus circle b plus circle c. Okay, now we will start proving this. So it is going to be a plus circle. What is b plus circle c? It is b plus c minus 1. So now this is my first element, this is my second element. So it is a plus the second element, b plus c minus 1, and you need a minus 1 over here in the definition. First element, second element, minus 1. First element, second element, minus 1. So that now makes it as a plus b plus c minus 2. Now we will work on the right hand side. A plus b is a plus b minus 1. So now this is going to be plus circle with c. So the first element plus the second element minus 1. So it is a plus b plus c minus 2. My LHS and my RHS are going to be the same. So what I have proved that associative law is going to be true over here. Now coming to the case of identity element. What do we mean by identity element? An element of the type A plus circle E, or that must be the same as E plus circle A, must give me back my A. So what is the definition of my identity element? By the definition, this is going to be my rule which is going to be satisfied. But how is the plus circle binary operation defined? It has been defined as A plus E minus 1. And now this has to be equal to what? Equal to A. So this A can be cancelled off over here, leaving me the quantity that the identity element is going to be equal to 1. So I have E to equal to 1 to be the identity element. So the next condition of identity element is also going to be true. And the last concept is going to be inverse. What is going to be inverse? A plus circle your b, which is going to be your inverse of the element A, is the same as b plus circle A, which must be giving back my E. If it is so, then B is called inverse of A. So my target is to find what is this B. Now how to define the A plus circle B? A plus B minus 1 must be equal to E. What we know about E? E is equal to 1. So what will happen? A plus B will be equal to 1 minus 1. If it goes to the opposite side, 1 plus 1 will become equal to 2. My target is to find my B. So what will be my B? B will be equal to 2 minus A. So whenever A is going to be my element, the inverse element of A is given by B, which is of the format 2 minus A. So now I have shown that inverse element also exists. Associative law is true, identity element is there, inverse is going to be 2 minus A. I have commutative law to be true. So with respect to plus circle, it is going to form an abelian group. So now this alone is going to be a package of an 8 marker for your group theory. Now moving on to the second binary operation, what we have is going to be the second binary operation A dot circle B, which has been defined as A plus B minus AB. Now with respect to my dot circle, I need to prove associative, identity and commutative law. So we will have to show associative, identity and I will have to prove commutative law. If I am going to show these three things, then my second part, that ring with identity and commutative ring with identity, will become true. So we will begin with the commutative law because that is going to be very easy of all. So when respect to commutative law, what we have is A dot circle B will be A plus B minus AB. So this is going to be this A and B we are picking up from the set of integers. So I can just rewrite this as B plus A minus BA. So this is nothing but my B dot circle A. So what has happened? The commutative law holds true for my dot circle. Next comes my associative law. What is going to be associative law? Associative law is with respect to three elements, that is A dot circle B dot circle C must be the same as A dot circle B dot circle C. So now we will apply the laws for your quantity. Now this left hand side I will start solving. A dot circle, what is B dot circle C by definition? B plus C minus BC. So this is my answer for my B dot C. Now what happens? This is my first element, this is my second element. When I do the dot circle operation, it is first element plus the second element and minus first into the second element. So let me do the operation. A plus B plus C minus BC minus AB minus AC minus into minus will become plus ABC. Now let me do with my RHS. RHS, first I apply A dot circle B, which is going to be A plus B minus AB, and to this I do the dot circle with C. So this is first element and then addition the second element minus A plus B minus AB, first element product the second element. So this will give me A plus B minus AB plus C minus A into C is minus AC minus B into C is going to be minus BC, minus into minus is going to be plus ABC. So A, B, B, C, C minus BC minus BC minus AB minus AB minus AC minus AC plus ABC tallies. So what we have proved? We have shown that LHS and RHS are going to be the same. Therefore, which law now becomes true? Associative law is going to be true. The next comes the identity element. So what is going to be my identity element? Identity element. So let me denote this identity element with respect to dot circle as my E dash. If I take this as E dash, A dot circle E dash must be the same as E dash dot circle A, must give us back what? The taken element A that belongs to the set of integers. Now how we have defined this dot circle? We have defined the dot circle as A plus B minus AB. A plus E dash minus A into E dash. This must give me what? The taken element A. So I have this A and A cancels off with one another. E dash minus A times of E dash is equal to 0. Take your E dash common outside. 1 minus A equal to 0. 1 is not equal to A, in which case what we have is E dash equal to 0. So now this E dash is going to be my identity element with respect to my dot circle. So I have proven that identity element also exists for this case. So the last part which I need to prove is going to be my concept for what is the last thing? Distributive law. So if I have proved abelian, I have proved that with respect to dot circle, it is going to be associative, identity and commutative. The last one is going to be distributive law. So if I am going to prove distributive law, then I am through. So what is going to be my distributive law? it is going to be A dot circle B plus circle C. So this will be equal to A dot circle B plus circle A dot circle C. So now come on, let us get started. So A dot circle, I am doing my LHS. What is going to be B plus C? By definition, B plus C is nothing but B plus C minus 1. Now you do the binary operation of dot circle. It is the first element plus the second element minus the first element product the second element. Okay, so it is A plus B minus AB. A plus B minus AB. So it is A plus B minus C minus 1 minus AB minus AC minus A. So this is going to be plus A and minus A cancels off over here, and minus of minus, this is going to be minus of minus A, this is going to be plus A. So you have A and A over here, so that makes it as 2A. There is going to be a plus B, and there is going to be a minus C over here. Okay, a minute, this is plus, so a plus C over here, B plus C, and then I have minus AB, and I have a minus AC, and then I have a minus 1. So let me mark this as my LHS. Now I will do the first part of my RHS, A dot circle B. So A dot circle B is A plus B minus AB. And what is my A dot circle C? So this is going to be A plus C minus AC. Now what I need to do, I do a plus circle with both of them. This is my first element, this is my second element. So this is going to be on a plus circle. I have first element plus the second element minus 1. So this is A plus B minus 1, which is the definition of plus circle. So I have A plus B minus AB plus A plus C minus AC minus 1. So I have a A, I have a A, so that makes it as 2A plus B is here, plus a C is here, minus AB is here, minus AC is here, and we have a minus 1 here. So that makes it my RHS. So I have shown that one part of the distributive law is going to be true. The next part of the distributive law is going to be B plus circle C with dot circle A, which is B dot circle A, and then a plus circle with C dot circle A. I suppose this I leave it for the readers to verify it for in the same manner as we have done. So if this is going to be done, I can show that Z, the set of integers with respect to plus circle with respect to dot circle, is going to be a commutative ring with identity, which is the other name for your integral term. So now what is the last thing which was missing over here was my identity element with respect to my dot circle. If I am able to prove this, then I will be able to show that it is going to be a field. So can we show that also, and then we will be totally complete with that. So what is going to be with respect to field? So A, if I am going to take my B as the inverse, sorry, not the identity element, inverse element was missing, right? So I will have to find the inverse element with respect to dot circle. Inverse with respect to dot circle. Let me take B to be the inverse element of my element called as A. Okay, so I know what is going to be identity element. Identity element is going to be 0. So I know that A dot circle B must be the same as B dot circle A must give me my identity element E dash. So A dot circle B or B dot circle A must give me the identity element. What was it? It was equal to my 0. So now I can take this as A dot circle B, which we define it as A plus B minus AB. So this is going to be A plus B minus AB. So this is going to be equal to 0. B minus AB will be equal to A, you take it to the opposite side. So this becomes equal to minus A. B, if I am going to take it common, it is going to be 1 minus A, which is going to be equal to minus A. So now this will give me B equal to minus A divided by 1 minus A. So the problem lies over here. What we have taken as the set, it is the set of integers. But what we get as B, the inverse element of your A, is going to be of the format P by Q. What does P by Q stand for? It stands for the set of rationals. Does rational become a part of the integer? No, not at all. So what happens over here? You don't have the B to belong to the set of integers. Therefore, we say that Z with respect to plus circle and dot circle is not going to be a field. Okay, so if this has to be a field, then this must be an integer. If I am able to get this as an integer, then very well I can show that the answer is going to be true. But since this is not an integer, now I can declare that this is not going to be a field. So now I have given you a complete package of the definition of ring and field and the example problem that deals with ring, integral domain as well as field. Whether that can be forming a field or not, what are the criterions to be satisfied and so on. I hope the concept for this elaborate example was very clear to you people and made the concepts fresh. So we will keep on learning. Happy learning, keep learning. Thank you very much.